Hello everyone. So we're going to move into the second section in your unit number 3. In this section, we're going to talk about the equilibrium problems. So equilibrium problems means basically objects going to be stable throughout the problem. So now in simple words, stay in equilibrium means basically there is no motion of the object, no motion in translational direction or no motion in rotational direction. So this is the starting point of the rotation that we're going to discuss, but more detailed rotational informations we're going to discuss in your next section. So now, if you have object at equilibrium, that object should have some conditions. We're going to use those conditions and we call it as equilibrium conditions to solve this kind of problems. Okay, so now we discussed about the Newton's second law so far. Now in says that there is no motion, definitely your right side, that means mass time acceleration of the object going to be 0. Because of that, your problems will be simplified. But since we're going to include the rotational force that we call it as torque, so there should not have any rotation also. Then we need to discuss about how to calculate the rotational force in this section. That is the new thing. The other things we already discussed in your Newton's laws. So now the content on this chapter will be included in your chapter 9. So let me share it. Chapter 9, right? So chapter 9 is the one that we're going to discuss now. And then let's move into the slides also. Okay, so as I mentioned, equilibrium will be very simple. Think about that you're going to stand on the floor. Then we can say you are at static equilibrium. Why? You are at rest. How it is rest? Because your force of gravity will be equal. I'm going to write f of g. So I hate to use this symbol, force of normal. So force of gravity and force of normal should be equal and opposite direction. Because of that, net force going to be 0. Then we can say, okay, this person is stable, and we can use the equilibrium information to solve the problem, right? So now these are the problems that we're going to discuss, but let's move a little bit about the equilibrium. Again, equilibrium means there is no motion. That is, actually we call it as static equilibrium. I'm going to talk about the static equilibrium only. So that means there is no motion of the object. That is called it as static equilibrium. So that means this kind of object sitting on the table, normal force equal force of gravity, then it is a equilibrium problem or static equilibrium problem. But if you think about you are riding the bicycle, you can say is still stable, but your wheels are keep rotating. In that case, there is a rotation. Then I cannot say your bicycle is at equilibrium. So we can say in one way it is equilibrium, but it is static unequilibrium problem. Okay. So now let's move into the conditions, because conditions are the main factors of this section for our calculations of problem solving. So now let's move into my right diagram. In right diagram, I have center of mass point here. So you apply the force to the left and force to the right. These forces are equal to each other. So when they are equal to each other, what will happen? So I have force acting on opposite direction this way, and cannot hold it this way and this way. We'll say they are 90 degrees, right? So I'm going to apply the force this way and this way. This object is going to stay at rest. That is what the static equilibrium means. Net force will be equal to 0. That means net force, this two forces will be cancelled out. That will give you net force towards x equals 0. And there is no net force towards y definitely in this diagram. And then you can say net force in x, y, and z direction are equal to 0. That is staying at rest. That is the equilibrium conditions. Okay. So now this is the new condition. What will happen if I have an object, but I'm going to apply the force on the top and the bottom? but I'm going to apply it in opposite direction, right? So I'm going to apply the force on this object, uh, this direction, this way, oops, and this way, right? I'm going to apply the force pushing this way, this side, pushing this way, and same side, I'm going to do the apply the force pushing that way. So now when I push object this way and that way, what is happen is this object going to move like this, right? You push in this way and push in this way, right? Then it's going to do what? It's going to rotate, right? That's what the rotation means. So now this rotation will happen on, in this case, it is happening on rotation in center of mass point, but rotation can happen in any point if you fix the object at one point. But we will come back to that later. But here, everybody, I hope, understand there is a rotation. So that rotation will have the torque, we call it as rotational force, that should be equal to 0 to have the equilibrium. That means this object is not at equilibrium, although my net force equals 0, I mean translational force equals 0, but there is a rotational force. Because of that, that object is not at equilibrium. Okay, not at equilibrium. Okay, so now let's move into the torque definition. So torque is basically rotational force. Torque is a twist or turn that tends to produce the rotation, right? That is called it as torque, and we have many applications and tools that we are using in everyday life. Okay, so now how do we calculate this one? So now torque is a quantity, that is a rotational force. That means there should be a direction, it's a vector quantity, and there should be a magnitude. So magnitude of the torque will be able to calculate by using this formula. What is this formula means? RF sine of theta. And before moving into the formula, let's talk about the units. You're going to multiply R and F, displacement and F, or distance and F. That will give you Newton's meters. Did we multiply distance and force earlier too? In your work done case, you remember, if I have object, if I apply the force, if this object move d displacement, then this object, we have done the work done, that is force times distance, right? But that also is scalar quantity, but it is the same units, Newton meters. Okay, in that case, this work done will be maximum when you have the force and displacement parallel or anti-parallel, right? If I apply the force in this direction, is object move this way, then there is no work done. So we discussed that detail. But here you have again displacement and force. Actually, it is not displacement, it is distance in this case, times the F and sine of theta. Let's talk about this little more. So now Newton meters is still unit. What you're going to do, we'll say I have object, right? This object, I should have a point that I am going to fix the object. That is, we call it as pivot point. Now in this object, my pivot point is this end, my left side, right? So somebody can take the pivot point somewhere else. Somebody can take the pivot point here. Then I'm going to keep rotate around that point, right? If I fix in here, I'm going to keep rotate around that point. So it is depend on the problem. You can give the pivot point in different places, right? So now let's see, if I have pivot point in this side, I am going to apply the force to this object upward direction, this way. So now if I hold my left side, when I apply the force to this object, what will happen? This will do in my side, it is counterclockwise rotation. In your side, you will see the left and right opposite direction. Okay, so this is counterclockwise rotation. Okay, so now I have two words in there. One is counterclockwise, that is the direction. I will come back to that in a minute. But magnitude that you are doing this rotation, turn or twist, you will be able to calculate by using or by times this distance time the magnitude of the force. That will be your torque, R times F. Okay. So now I did not get the sine of theta. What is the sine of theta mean? Sine of theta is angle between R and F. In this case, what is the angle between R and F? It is 90 degrees. I mentioned this many times. When the sine of 90 degrees value will be just 1. That's why in this case, it is just R times F. That is the maximum torque that I can have, right? So where the sine theta coming from, if I have the force, something like this. Now this is the force. When I apply the force, it's still my pivot point here. Is still my distance is the same, but I tilted my force. Now I keep applying the force. It's still doing the rotation, but this torque is less than the torque I had when I apply like this. This is easy rotation. This is little hard rotation. Because of that, your rotation will be less than that. In less than the earlier case, then I need to consider this angle in between R and F to your equation. That will be always less than the 1 value. Then you will be able to calculate the torque. Okay, so now let's talk about the direction. So now let's come back to this problem again. So now how do you find the direction of this torque? So you can say it's counterclockwise, clockwise, depend on the problem. You can say inward, outward. It is the direction of the torque. Now in this case, you see that when I apply the force by fixing this point by pivot my left side, I'm going to apply the force in this side. Then this will do the rotation. We call it as counterclockwise direction rotation. That is by conventionally, that is the positive torque that we are calling it as, because it is in C direction. Okay, so counterclockwise rotation. Now if I have an object, if I apply the force downward to this object, downward, now what will happen? Now it will do clockwise rotation. Now it will do the clockwise rotation. Because of that, that is the direction of the torque. Okay, so now we have idea that clockwise torque will be negative. Now let's move into this problem. I have a force applied in here, and I apply the force in here. Now what will happen to this object? Do everybody understand this object is rotating clockwise direction? It is something like this. You have force downward, upward, right? So downward, upward. Then this will rotate clockwise direction. So that is what the clockwise means. Okay, and that will be basically, if you take your screw, that means you basically tighten your screw, you tighten it, right? Because always when you need to tighten the screw, that means you're doing clockwise rotation. Okay, so now other case, you're going to apply the force downward this direction, upward this direction. Now this one doing, see, upward, downward, doing counterclockwise rotation. So that means you have this symbol. That means you basically release in the your nut or screw that you are using. Okay. Okay, so I think you're going to solve a couple of problems in your recitation session. Basically, it will be this kind of problems. And everyday life torque is very important concept that we're going to use when you lift in the objects. So you know that this is the best way to lift it, and this is not the good way to lift it, because it will give you the torque that you cannot handle from the bones, and then it's going to damage your bones in the body, right? Or muscle in the body. And so now this is one example that when you lift up 50 newtons weight ball, then there is a actually pivot point. In this case will be this, because you have elbow, then you're going to lift it up, right? And then when you have that, you are doing this distance time the force in here, so that will going to create a reaction force on these biceps. So otherwise, because it should be equilibrium, right? So then it will create the reaction force on the bicep that you can calculate by using that. And in addition to that, this problem also you're going to check with 9.5 example in the textbook. And there is a box that this guy is lifting up, but there is a bicep force, that FB that I have, this FB will be created by somewhere here. right, on your back. And then there is a upper body weight that act as here W you see, and there is a weight on the box. These two will do the rotation with respect to your back. They are doing this rotation. They are doing the clockwise rotation, but your FB, that the back bone pose, should be doing the counterclockwise rotation to make it stable. Right, so, and also you're going to definitely do your ruler balancing problem in the your laboratory by applying force in this direction, and you're going to balance. You're going to seesaw the by using the ruler. So those are you're going to solve during the your recitation session. And I have simple example here. Everybody know how the seesaw will work, right? If I have 30 kilogram boy and 25 kilogram girl, and if this is the pivot point, then if boy is sitting 2.5 distance, what is the distance that girl should sit to make the seesaw balance, right? That is basically you are using your net torque equals 0. That is the equilibrium condition. Then you're going to write torque counterclockwise is equal torque clockwise. That's it, right? Then who is doing counterclockwise rotation in here? So if you draw the free body diagram, this is the free body diagram. This is the force by girl, this is the force by boy, and those are the distance. This is the pivot point. There is reaction force similar to the force that if I have this reaction or normal force will be equal to the adding of 3 forces I have it in down direction, because one equilibrium condition is net force equals 0. That means Fn should be equal to Fa plus Fb plus m times g. That is the weight of the beam that you're going to see. So now, but that's everybody know how to calculate it because it's very simple calculation. But torque is the one that I'm focusing in here. So counterclockwise torque equal clockwise torque, right? What is the counterclockwise torque? Which one doing counterclockwise torque? So you can see this force doing the counterclockwise. This is something like that. You're going to hold in the middle, and there is somebody going to sit on this side. When somebody sit in this side, this is going to do the rotation counterclockwise clockwise in my side, right? Clockwise direction in my side will do the rotation by girl. So now if somebody going to sit in this side, is going to rotate counterclockwise. That means counterclockwise doing by the boy, that will be the Fg of the boy, that is ma times g, force of gravity, and distance to that is already given 2.5, should be equal to mb times g, that's the force of gravity of the girl, times distance is x. Right? So now you can see g and g will cancel out. You can calculate the x. X will be ma over mb times the 2.5. So now MA and MB are given, then you can calculate the X. In this case, it is 3 meters. Right. So that's how you're going to use the second equilibrium condition. So that is the new one. But the other one, as I mentioned, net force, there is no force in X direction at all. So net force towards Y direction should be equal to 0. That is the first equilibrium condition. In this case, that means normal force that I have it on the free body diagram is a positive number, other all are negative. That means I have Fa plus minus Fb minus m and g, because of the beam should be equal to 0. Okay, that is the first equilibrium condition. So those are the 2 equilibrium conditions that we can use to solve the problems. Okay. I have another example here. You're going to do exactly same kind of problem in your class, but I'm going to start it. You guys can discuss it that in your recitation. So I have a uniform beam of mass MPG, that is this one. So make sure that given information is gram, you need to convert into kilograms and then times the gravitational constant that will give you the pose, the things that we learn in first week, right? And then length is given L and 1 meter. And the shown in the masses, M1 is unknown and M2 is 200 grams. And the end, if D is 25, calculate the mass of M. I'm just going to use the symbols that you guys can plug the values later. So now, since it is asking mass M1, so, and also in this problem, pivot point is given in here. If pivot point is not given, you can select the pivot point because it's stable means your beam is basically horizontal, right? So now you're going to write at the pivot point, net torque is equal 0. That means counterclockwise torque should be equal to clockwise torque. So now you need to identify which one doing clockwise, which one doing counterclockwise with respect to your pivot point. So now you can definitely see this one doing the counterclockwise. Similar thing, you holding in here, then you going to add the weight in here, this will do the counterclockwise. And then your MP somewhere here, going to add the weight, doing counterclockwise. But if you have weight in here, this will do the clockwise rotation. Okay, so now counterclockwise rotation will be from M to G times the distance to that. You see that it is twice of D. Okay, in addition to that, you have MPG that also have the torque, but I need the distance from that point to this point. So that is also given half D. Then D over 2. Okay, should be equal to clockwise. Clockwise doing by this. That will be M1G. Distance to pivot point from that is D. Okay, so now you see that G will cancel out and D also cancel out, right? So then you will be able to calculate by plugging the given information. You will be able to calculate M1 from the problem. Okay, that's how you do it. Okay, so again, in your recitation session, you're going to solve this kind of problems. Definitely this one is there, definitely this one is there, this one is there, and this one also there. So other things may be not there, but those are different kind of problems that you can work with, right? And this will be a very simple example that you can think by using your knowledge conceptually. You have the mass 1 kilogram here, and there should be a mass here, but it is balanced with respect to this point. Then this mass times this distance should be equal to this mass times this distance. Then 3 times 1 is 3. That means this should be basically 3 kilograms. Okay, so after you go here, you're going to balance it from here. That means you have 3 plus 1, 4 kilograms basically here in 1 meter. 4 times 1 is 4, and 2 times 2 is 4. Because of that, this will be 2 kilograms. A conceptual question that you can easily think by using counterclockwise and clockwise rotation. Okay. Okay, so now stability and the balance. Stable equilibrium means if I keep the pencil, that if I am able to keep it like this, like you are standing on the floor, something like that, that will be normal force equal force of gravity. In that case, there is no rotation and there is no net force, then that is stable condition, right? But there is very important information in here. But why this pencil is not stable? Which is called it as unstable. Because you see that you still have the forces are equal and, excuse me, opposite, but there is a rotation. How rotation will work? Because you see that rotation happen because your center of mass point is not actually contact point. That means your center of mass point is unbalanced. It's not exactly on your vertical axis. If center of mass switch into the left or right, then your vertical axis, then it is unstable equilibrium. Okay. Okay, so the other case, you can think about the refrigerator. If center of mass align with that your contact surface, your normal pore space, that is stable, and this is unstable, this is unstable. And also you can see here, this is stable, this is also kind of stable, but this is unstable by carrying the bag on the one soldier. Okay. Okay, so that's it for this section. Make sure that you attend the recitation and work on the problem very carefully.